So we're just going to wait here for a moment as people arrive and just let them know to head over. Hey.
Hey.
I also have a little sort of intro to the event that I want to be sharing as a starting point. So I'll get that set up. Yeah, I'm wondering, does someone want to head over to the Discord just to let people know that we've started, just in the Lisbon chat specifically? Just let them know that this is kicking off and maybe share the link. I think that would be awesome. And we will say to everyone else as well. Okay. Nice. Yeah, so maybe just to give some context. So we're just using Hopin, which is like a platform that we use often for the online ZK hacks. There are two chats. There's an event chat and a sessions chat. People are often like mixing those up. Stick to the sessions chat. Also, don't click the blue button that says share video unless you want to come on stage, because that's what you're doing when you click that. So just kind of leave it. Yeah, we're just going to give folks a little bit more time to arrive. The goal of this is to kind of, we just thought, given that this is the first time we do a ZK focused hackathon, given that like ZK in general is it's been in such a kind of tool building mode for so long, we're only now getting to the point where we can like start to really build applications with the tools that have been built. We thought it would actually be worthwhile for us to do a little bit of a prep session where we share links and resources and maybe some like ideas for how to even approach building in this context. A while ago, Kobe and I did a Twitter Spaces where we talked about use cases. And I know that we've shared in our Discord like a bunch of links and ideas. I've also seen some other folks sharing ideas there. That's awesome. Just to like kind of start thinking about what we can actually do. This is something that's going to be a group effort. And it is our first. So we hope we do more of these after. But like, yeah, we kind of recognize it as like it's a first of its kind. So we're all learning together, and we're going to try to, build cool stuff in a short period of time with ZK Tech, which is, a real challenge. All right, I think we have a good group here. I wonder if, I can go through these slides. Agni, do you think, is Thor already set to come up?
No, not yet. I'm just asking him to press the blue button. This is the only person that can do it.
Press the blue button. Nobody else should press the blue button.
Yeah, he's all set to come out.
Cool.
I added him to the stage as well.
Okay, good. That's awesome. Yo.
Hello.
Okay, so I have. Oh, are you wearing the shirt?
Yeah, I'm wearing my shirt. Got my ZK hack shirt on.
Very cool. I think we might have more of those, hopefully, at the event.
Let's see.
Anyway, but okay, so I'm just going to go through a few slides. This is actually a bit of an intro to the event, just so you know, like a little bit better what to expect. And we will be sharing this video afterwards on the YouTube channel as well. So like, we can, if you want to revisit anything, you'll be able to see it there. So I just want to introduce you a little bit to our team. This is the larger team. You see a few folks in the chat: DC Builder, Hector, I don't know if he's here today, Natalia, Kobe, Antec, and on the stage here we have Agnieszka, Thor, and myself. So we will be there at ZK Hack Lisbon, and it's been really fun and interesting to learn how to put this together. Thank you all for being kind of patient with us too. This is the first time we do it. So yeah, appreciate you going through this with us. So the event will be held at this kind of amazing, beautiful, magical venue, which is the Academy of Sciences of Lisbon. And I don't know if anyone went to ETH Lisbon last year, not the one before, but like just in 2022. But that's where it was held. So this is the second time that we know that this venue has done a hackathon, which is great. And we're getting a chance to actually do our event there too. I think you should all have the address. If you don't, obviously get in touch with us in the chats and stuff. I want to share a little bit about what we expect in terms of an audience. So we think there's going to be around 150 to 200 hackers in attendance. We have noticed that there are different levels of experience. There are some of the like best applied cryptographers in the space will be hacking, probably building some very advanced tools. And there will also be, I think, some people who are still kind of getting their footing in just the concepts of ZK. It is a technical hackathon, though, and ZK tooling is still not very user-friendly. So I do think if you can do any preparation, that's probably a good thing, just so you come not sort of overwhelmed by sort of the level of these tooling. So you have some sense for like what you're going to be working with. Yeah, and then we have about 30 mentors and, did I spell that right? And sponsor guests, as well as I think 20 or so team members and volunteers. So this is our rough kind of sense. We think it's going to be somewhere between 200 and 250 people. There might be a few more guests sort of floating through, but like, yeah, it should be a pretty like, I don't know, not too big event. I think you should actually be able to meet a lot of the people. A lot of folks have asked us about the DevFolio tool. A lot of people have complained about the DevFolio tool. So DevFolio is a Web3 native hackathon platform that we did decide to use kind of early on, but it's a very new platform. And so at times it's been tricky to use on our side, not so much like flexibility and what we can do after it was live. We're doing our best with it. I know a lot of you are registered there. That's the tool we're going to be using for this one. We were kind of testing it out. I think it has its benefits. And yeah, I think if there's people who really don't want to use it, we do have some workarounds. You just have to get in touch with us and we will like basically take note. But I think a lot of you are signed up here and you can also join teams here and we can like share the prizes and everything should be actually quite well articulated through the platform. But I just want to give you a heads up as to like why we are using it and how we're using it and where it might be clunky. And I hope you'll bear with us.
It can't be clunkier than the one they had at ETH Denver, which was crashing and like not allowing submissions and not allowing judging results.
What was that one? Was it DevFolio?
No, it wasn't DevFolio. It was a fresh baked one that was just crashing the entire weekend. It was horrible.
Oh no. Well, hopefully we don't have that problem. But we are kind of like, I mean, our team, I think we're ready to fight fires and make this thing happen. So could also be fun. So what can you be doing at ZK Hack? I think if you even look, and I'll try to dig this up, but like we did do a list of potential projects and some of these were actually building in ZK tooling for different systems. So if you are more advanced and that's something you want to do, that could be a project that you do for the weekend. You could be using some of the DSLs, experimenting. And then obviously what we really want are these new product ideas, applications that actually showcase what ZK can do. That I think if you look at like how we're going to be judging overall, it will probably be a little bit more like heavily weighed on the application side, just having cool applications that people could potentially imagine using. But obviously, if you're building really cool tools, there are also ways for you to get kind of rewarded for that. Yeah, while you're there, you get to meet teams who are working on ZK. You can learn new skills, find your collaborators, friends, and hopefully think up new ideas that we can use ZK in the real world. Here's the timeline. So the overarching timeline is Friday, we have our kickoff, dinner, and team formation. Saturday, we hack. We do our sponsor workshops throughout the day. We will be providing lunch and dinner, but like the area where this venue is has tons of restaurants around as well if you want to pop out. And then on Sunday, we're going to be doing our judging. We're going to serve a lunch. We're going to be giving out prizes. And here's a little bit more of a breakdown. At 6 p.m., we start the opening ceremony. At 7, we do dinner. And at 8, we're going to be doing team formation and hacking. So it starts later in the evening on Friday. On Saturday, we have workshops all day long. We start at 10 with Risk Zero, Sysmo, Polygon. We're doing a privacy on Polkadot via XCM workshop with Moonbeam, as well as potentially some parity people. And we will also be hearing from our partner, Aleph Zero, at 4 p.m. a.m. No, 4 p.m. I'm definitely gonna need to fix that. Sorry, yeah, there's some, I just realized this was not updated with proper, yeah, this could be better. Okay, we'll fix this. I will be using the same slides from my intro next week, and those will be corrected. Okay, on the actual day of submissions, this is potentially going to change a little bit, but our idea is 10 a.m. submission, 11 o'clock judging, 1 p.m. Lunch, and then we will close the ceremony. We will close down the event through ceremony and prizes. The workshops are about 30 to 40 minutes. It will be partners showcasing their tools, and they're going to be also sending expert teams to help you out. A bit about the bounties. So we have sort of two types of prizes. We will have like partner bounties. So those are like if you build the ZK tooling with one of the teams that are there, they're going to actually give you really clear outlines. And that is a kind of a nice way for you to be able to contribute like real tooling to the community and be rewarded. And then we're also going to be doing the general prizes. And what we plan on doing is a top 3 of all projects, as well as a hacker's choice. We're going to try to do like a poll of the community and see. We don't actually know how to do that yet, but hopefully that'll work. All right, I think that wraps up the intro to or the sort of like look forward at what to expect from ZK Hack Lisbon. And now I think I'd like to pass it over to Thor, who's going to actually be sharing a little bit more about some like examples. Oh, and one last thing before I do it though, I have a list of links, useful links for all the partner projects. So if you want to do some pre-reading for those workshops, follow that link. I'll just put it in the chat right after this.
Awesome. I am very excited for all of the hacking and all of the things. And I have also prepared some links and an introduction to some things that you might think about with circuit programming. So I'm going to do a screening of sharing, and oh no, okay, so how do we figure out which screen to share? Okay, we figured that one out. Okay, there we go. I pressed the button. Right, ZK circuits for great good. Yeah. So the sort of thing that we're going to be talking about is this lecture is sort of directed towards folks who might not have as much of a background in circuit programming and might be coming in and thinking, well, so I'd like to write something for this hackathon, but I haven't actually seen all of the tooling, or I haven't been able to write these circuits before. So this is going to give some motivation of things that you might be thinking about writing your circuits for, and some of the tools that you might choose to build those circuits, and sort of where you might expect to deploy those circuits is going to matter a lot. So you might ask yourself, why would I write a ZK circuit? And there are a couple of reasons. So the first one is that it's an easy way to preserve, or it's a fundamental way to preserve user privacy, especially in a peer-to-peer context, but in even a client-server model where your client has some data, like their identity, or some computation that they're doing, or some private transactions. There are lots of things that you might use a ZK circuit to do. So identity is a pretty big application area, and I think it's going to be relatively important because there are lots of types of things that you might like to do with identity. So Sysmo, for instance, is a project that's introducing a circuit system, or a system basically to prove that you have some particular set of identity. And you can do this in such a way that a smart contract can verify that you are who you say you are, or a TypeScript verifier can also verify it. So Sysmo is written in Circom. And Circom is a circuit writing language that we'll see a couple of examples here in a couple minutes. So if you were looking to, say, allow the user to compute some proof and submit that proof to a verifier, either in a web app with a sort of TypeScript backend or to a smart contract, you might choose to choose Circom or Noir, which is another circuit programming language we're going to be talking about today. So the second reason is that you might like to have server privacy or validity. And so the kinds of applications that we're building for preserving user privacy and validity tend to have a slightly different model than server privacy or validity. And usually the case is that if we have the user is assumed to have all of the data, we we will have the user compute the proof. But if the server actually is, say, a supercomputer, which is the sort of thing that rollups do, where all of the proofs or all of the state transitions are computed by a large central computer, and then you can decentralized verify that. We can have server privacy and validity, where the server, usually we care more about validity in this context, because we're binding the server to some computation. And a sort of like closely related analog that is P2P trustless execution, which is sort of what I was talking about before. And so an example of here is that if we want to trust a bridge to basically compute a Merkle inclusion proof, which is what we're actually going to be covering today, we can have a ZK bridge give a zero knowledge proof that some transaction was included in the header of a blockchain. And the same thing kind of goes for how rollups work. So that sort of is a quick overview. And the next question is, well, how do I pick a language that I would like to use for writing my circuits? And so I've prepared a couple of code examples for you here. And let's grab this, and I'll post that in chat. And oh, interesting. It looks like I just posted as if I was logged into. It looks like I posted as Leo. That's fascinating. Okay. Hey, Leo, I'm you now. That's fascinating.
That's so weird.
Yeah.
That's great.
Wow.
Huh.
Well, it's like extra fun that Leo was in the chat to capture my stealing his identity. You thought you were the master of identity, but I'll show you. Yeah. So there's some circuit examples in the chat. That Leo helpfully posted. So we're going to switch over to talking about first Circom, and then we're going to cover a Noir and a RISC-0 implementation. And I prepared two examples in each language for you. One is a fairly simple example of just preparing a circuit that computes the dot product of two vectors. And the more complicated example, and a very useful example, is a illustration of how you might do a Merkle inclusion proof. And Merkle inclusion proofs are used for all sorts of things. You can use it for, well, of course, we use it for proving that a transaction was included in a blockchain, but we can also use it, and for instance, Sysmo uses it to prove that a person is included in a set without revealing which member of the set that is. So I could, for instance, prove that I have some NFT without revealing which NFT I hold, or that I am in some set of users that are stored in a Merkle tree. So the basics of Circom require you to think like an assembly programmer. And if you've worked in mostly high-level languages, like Python, or we'll even call Rust a high-level language for this purpose, thinking in circuit programming requires you to think very much like, okay, so what are the inputs to my gates and what are the outputs to my gates? And so to do a dot product circuit, we might expect that we would want an input vector and a pair of input vectors of length n. And if we wanted to say compute this dot product and also bind it to some expected value of the dot product, we might also include an input called expect. And then finally, our return type is going to be called an output, which we'll call out. So we're going to simply say with two input vectors and an output vector, and optionally an expectation if we wanted to bind the output to some expected value. We would say, shoot, thank you for speaking up. It looks like the screen sharing requires me to change the screen I'm sharing. And we have, that's the one. Click that. Yeah, sorry about that. Thanks for, yeah. Can you see my screen now?
Yeah, we can see your screen. Also, how did Leo just talk to you? This is pretty amazing that it was Leo who pointed that out, as well as, yeah. Wow.
Yeah, and I am logged in as myself. So this is a particularly fun cookie or Easter egg in our identity software. It says, Leo says, also it says that I am Thor, but chat says that I am Leo. And you, wait, someone else says that they are Thor.
Whoa. What is
okay.
happening? Whoa.
So,
okay. We broke Hoppin, clearly.
Okay, yeah, we're killing. Oh shit. All right. Yeah, I think I might have popped off there for a second. Am I good?
You're good.
Okay.
And we can see your screen.
Okay, cool. Yeah. Well, that's a fun adventure. This is what happens when you use ChatGPT to write your servers, guys. Maybe that's a long joke, but back to Circom. So with Circom, we basically need to think in this sort of like gate specific way. So if we had two vectors that were our inputs, we would say that those are our inputs, and maybe we expected some output optionally, and we wanted to say this dot product is going to produce an output. And we would program the dot product in such a way that we would actually need intermediates. So we need to do two steps to compute a dot product. First, we need to multiply each element-wise pairing in each vector, and then we need to add it all together. So we're going to say, create this intermediate signal called products. And we're going to use a sort of intermediate set of gates, these multipliers.
Could you make the screen a little bit bigger? Because there is we don't see it very.
Yeah, let's do that.
That's great.
Thanks.
Thank you.
Yeah. Awesome. Thank you. We would basically need to say, well, we're going to need a bunch of intermediate multiplier gates to multiply all our elements together. And so we may loop over creating a bunch of multiplier gates, assign to the inputs of the multiplier our element-wise pairing, and produce a product. And then finally, at the end of the circuit, we'll have a vector of products, that we can add together. So we're going to need two subroutines in this circuit, or three rather. We need a circuit to add two elements together to build our circuit that adds n elements together. And then we would need our multiplier gate, as we said before. And so things that help when thinking about Circom is sort of like this frame of mind that you're writing specific gates, and you can't overwrite gates. You might think that you might just think of all of your gates as immutable variables. And so in some ways, you're sort of functionally programming, where each of these left assignments is your sort of only assignment. And this isn't entirely true. You do have variables like I in this for loop that can change. But when you're programming in Circom, it helps to think of your gates as sort of immutable. And maybe you use a mutable intermediate variable. But the sort of thinking when you're whiteboarding this out is that you should have some idea of what gates you're going to need to grab, in this case, an adder of n elements and a multiplier of 2 elements in order to make this dot product circuit. And so the next circuit example, before we move on, if there are any questions about that, feel free to throw them out in the chat, and I'll try to answer them as we go along. So the next circuit example comes from Sysmo, and since I am now Leo of Sysmo, I am now apparently the author of this code. The premise here is that we're going to talk about a Merkle tree. And if we My bad. I think I seem to have gotten. I tried to stop sharing screen and share a different screen, and I think it kicked me off.
Full rug. Okay.
So I got rugged. So if we're going to just cover what a Merkle proof actually is, it would be good to sort of just quickly run over what we're trying to do when we create a Merkle proof. So in a Merkle proof, and this might be review for everyone, we need to say, well, here's a tree, and each element higher in the tree is going to be the hash of each element just as its children. So to prove the inclusion of element 5, we need to provide the parents, the direct parents of the child. So if we were to say how to create a tree, well, with a vector of elements n2 through n5, we put them in the tree, we compute n0 as the hash of n2 and n3, compute n1 as the hash of n4 and n5, and compute the root as the hash of n0 and n1. Now, it looks like there's a question. Why do we want to write a circuit directly and not have it generated by writing in a higher level DSL? Well, I think we're going to cover some other higher level DSLs here in a minute. But one reason to write the circuit directly is sort of an analog to why write assembly directly. And the basic reason is control. When you write in a higher level analog, what you're going to get is the compiled result of what the higher level language is going to try to produce for you. And in a lot of cases, I think that's sort of like the kind of question where I would answer that if you are writing in a high-level DSL and you aren't getting the performance you need, then maybe you look to lower-level DSLs. But since Circom came first in the historical sort of emergence of ZK programming languages, ZK circuit languages, and is probably the most popular ZK circuit language, I wanted to cover it first. Now, the second examples in Noir and RISC-0 will give you a higher-level DSL. Noir targeting a lot of the same targets that Circom has, and RISC-0 being a full extension of the Rust programming language, which is quite powerful, especially if you already speak Rust. So back to Merkle tree proofs. What basically we need to do is we need to have, given some elements and an element that we want to prove inclusion of one, we need to say, let's construct this Merkle tree proof. Now, we're going to see if this kicks me off when I try to switch the window that I'm sharing. Hopefully not. Okay, cool. We did not get kicked out. That's great. Now, switching back to this guy. So this example comes from Sysmo, courtesy of Leo at Sysmo. The thing that we're going to need is, well, we're going to start by saying, let's talk about what a verify Merkle path struct might look like. Yeah, Leo, you're on stage. So we might say that the first thing that we want is we are going to want to prove that some leaf exists. And since the sort of end of our proof is going to look like the root, we're going to have an input of a root. And then finally, we're going to have a vector of elements along the path. This was the path from the root to N5 and their indices. So we're going to need basically to loop over this path. We're going to take advantage of a subcomponent called position switcher. And what the position switcher just does is it says that if the input S is 0, return 0 in 0, 1, and if it's 1, return in 1, 0. So it's basically an indexing switcher, where if we take in this vector of ins, it's going to give us the permutation of those elements. Now we say we need the element that we're proving, the root, and the path of the elements and their indices. And to compute that, we're going to say, okay, so we're going to need some intermediate circuits, the selectors and the hashers. And the selector levels and hasher levels are the intermediate components that are going to hold on to our circuits. So the selector holds on to the position switcher, and the hashers holds on to the outputs of the selectors. Now, there's a bit of indirection here, or there's a bit of using the Circom library here. We need to pull in an actual hash function. So Poseidon is a hash function that's specifically designed to be used inside of Merkle trees, inside of zero-knowledge circuits, because traditional hash functions are not particularly efficient. So we're going to need to pull in the Poseidon hash function and then these two other libraries that are sort of helper libraries. And what we basically do, and this might not be the super clearest, it might be more clear in the follow-up examples, is that we're going to say, take a look at the leaf and evaluate whether the index is correct, and then extract the leaf elements along the path, and then compute the hashes. So this hasher function is effectively going to compute the hash of these inputs. Now, I don't want to spend too long on the circumlib example, but since Leo is in the chat, if you have any further questions about this particular example, I think that would be a great place to ask them. We're going to move on now to talking about the Noir language. So the Noir language, we have the same two examples, the dot product and Merkle tree. So Noir looks a lot more like a high-level language here. We start by declaring a, I sort of skimmed over just a little bit the step of actually declaring our inputs in the Circom example. In both Circom and in Noir, we need to declare our inputs somewhere. And I am kind of skimming over the build process, but in Circom, we declare our inputs in a JSON file and the expectation value for the dot product. And then we can run our proof and build and check whatever it is that we're checking. In Noir, we do something pretty similar. We say declare, just as before we declared inputs in a input.json. This time we're just going to declare our inputs in our prover.toml file. That's the wrong inputs. Let's go here. There we go. And then we say write our dot product, and we can use, as before, we can use a function inside of our main loop, and our program is going to look for our main program, load it with the inputs from prover.toml, and evaluate the function. And Noir looks a lot more like a high-level language. You don't write the circuit specifically. You write in this Rust-like DSL. And you get to take advantage of a sort of more traditional C-like language style. And another pretty significant advantage of working with Noir is that they have this inline testing. So you can write tests basically in line with your actual code here, while the Noir or the Circom library requires you to write tests in JavaScript or TypeScript. So this is what I would say is like a fairly ergonomic flow if you were looking to reach for a higher level language that's probably quicker to get off the ground. The language should be pretty familiar to you if you already have written a little bit of Rust. And the only thing that might be particularly unfamiliar to you is this language of field. And since all of our elements are coming from a finite field, that is the integers modulo some prime, you can think of the word field as a really big integer, or an integer that can be up to really big. Where really big is probably on the order of 2 to the 256, although I haven't checked that. So just take it as a really big integer. And to compute our dot product, we basically just need to write this reasonably high-level program. We multiply our element-wise vector elements and add it to our accumulator vector, or our accumulator element out, and return out. And then we can say compute out in our main loop. And maybe we want to print some nice print statements so that we can sort of see what it does, or we could just take those out if we would like. But the print statements will not be in our final circuit, so we can put print statements in without having to worry about losing speed in our final executable. And then we can finally prove our circuit. Now, conveniently with Noir, as we move on to the next example, Noir has a pretty developed standard library. In fact, when I looked for an example of the Merkle inclusion proof, which is something that you probably will be doing at least once while you sort of work on your circuits, it is convenient that Noir has in their documentation an example and in their standard library a check membership function for checking membership of Merkle tree inclusion. So this means that you can really just rely on the standard Merkle check membership method for any sort of thing that you might do this for. Now, if you were to go look at the documentation for this this method, you might see that it's tagged with a decorator that says foreign Merkle membership. And that means that they're actually calling out to a Rust implementation that does a more efficient check membership implementation. And I'm not sure if that is accessible to developers yet. But if someone knows the state of Noir development, whether you can write foreign Rust binaries that can be then included in a Noir proof, do you post that in the chat? Because I'm quite curious. So back to this example, the thing that we're going to do is we're going to say, take some commitment at some value in a Merkle tree, hand our check membership the root of the tree, the index of the leaf and the path, and have the Merkle tree compute the inclusion proof. And we can say if the root of the tree is equal to what we expect the root to be, then we can say that the Merkle tree has succeeded. Sort of takeaways from Noir, I think, would be that when working in, and as the question earlier asked by Slava Marlow, why would you choose to present or to write a lower level circuit? I think the reason is that you might have a little bit more control over exactly what is in the circuit. However, I think for sort of getting up and prototyping over the course of a hackathon, a lot of the time speed is of the essence. And so you might choose to work. I think this might actually, there was a question in the chat, what does the constraint root equals root actually do? So what I should have actually done is let this be the thing that I wrote so that it checks root equals root underscore. Because this would check the expected root versus the computed root of this Merkle tree. And then you could say compute the, or check that the root equals root holds as your constraint. But yeah, to finish that thought, the sort of language that you choose to write circuits in, especially over the course of a hackathon, might be choose something that is higher level and see if you can get to sufficient performance. And I quite like the documentation for both Circom and Noir, but Noir definitely was easier to get started with. But would what, and there's another question, but would what you wrote still work because of shadowing? I think that would actually have not worked because it wouldn't be checking that this root was equal to that root. It would have been checking that this root was equal to itself. So that was a demo bug, shall we say. Now, last but not least, this is a sort of increasing levels of how much sophistication you can put into your circuits. Noir is a low-level language, or well, Circom is a low-level circuit writing language. Noir is a circuit DSL that is a little bit higher level than Circom and gives you access to some of these sort of standard tools. But what if you wanted to do something that required, like, say, a sort of whole standard library of a complete programming language with a fully developed sort of ecosystem of tooling? And you might want to reach for a standard language that sort of has tooling already for it. Well, then you might be interested in reaching for RISC-0. Now, to answer a question for Leo, where do you specify the depth of the Merkle tree in Noir? And yeah, so I think the depth is implicit in the hash path variable, which there's a 3 element array here. So that says sort of implicitly how deep the Merkle tree would expect to be. So the last example that I'm going to show you is RISC-0. And if you're familiar with writing Rust already, RISC-0 should not be too hard to pick up for you. Basically, you need to say, create 2 separate crates. One is going to run inside of the ZK prover's head, and the other is going to run publicly. And so inside of the ZK prover's head is, they call this the guest. The prover is the guest that does the private computation. And so if the prover was going to compute something like a dot product, the prover would basically say, okay, so go reach inside of this methods guest area and have the prover do the computation that they're supposed to do. Read any arguments handed to it from the public end of things, and then finally compute that product. And one thing that I would like to point out that is convenient about RISC-0 is that we can get deserialization working relatively simply by saying just declare a struct that serializes with CERD. And this will make sense to you if you've worked a bit with Rust or done serialization stuff. This is trying to answer the question, how do I pass information back and forth between the prover and the verifier? Well, have the prover construct some arguments that it hands to the verifier and have the verifier deserialize them. And then finally, yeah, CERD. You can also say CERD. And have the verifier take this set of arguments, which in this case is just 2 vectors, and run them through a deserialization, do whatever computation that you'd like to do, assert whatever you'd like to assert. And this is basically what you would expect to do for the verifier. So maybe the prover is going to check the assertions that the verifier is going to check before committing back the result. And then when we get back to the result, the thing that the public guy is going to run, the public guy is going to say, I'm going to build some arguments to go hand to my my prover. My prover is going to do some computation, and he's going to hand back a result called a receipt, and we can extract whatever the prover had to say from the receipt, and finally we can say I have a dot product of 2 vectors. And to verify the receipt, very simply, you can just say call out to verify, and that just works fine. So this is a sort of simpler example. Now for the more sort of involved example of a Merkle tree. There's one thing in particular that I'd like to highlight here, and that's that you can define the struct that you not only want to hand into the private environment. You can define not only the struct that you want to hand into the private environment, but the string you want to hand back. So the thing that we're going to hand back is a Merkle proof, and our proof is going to come from our kind of simple Merkle implementation. And this is borrowed from the RISC-0 documentation. There's an excellent example using a Where's Waldo sort of context where the prover wants to prove knowledge of what bits within an image Waldo is, and they use a Merkle tree to commit to all of the bits within the image. We have a Merkle tree that comes basically from some dependencies. Specifically, Merkle light is the crate, if you want to take a look at that. And we can simply say call out to our dependencies and go, where we go? Here we go. Go import some dependencies, use them to build our Merkle tree, write a wrapper proof, which just wraps around the proof from our given library, and we can compute a Merkle proof inside of the prover's head. So this is our shared library, our core library. So now to see where we're actually using that, we would go over to the prover's head, which is called methods guest. The prover is going to read the private inputs, get the item to prove, build a Merkle tree, and of course we could say also have the prover read the Merkle tree from their environment. Maybe we cheated a little bit here by having the verifier hand the Merkle tree to the prover. We could also have the prover read the Merkle tree from the environment and have them write it to a file or something. Prove the thing, generate the proof, optionally verify the proof, and hand back the thing that they're going to hand back to the verifier. The verifier comes back over here in, where were we at? We're in methods. We want to be in host. And finally, in our public verifier that's going to hand things to the prover. We just generate some stuff to throw in a tree, pick something that we want to prove the index of, and commit our inputs to the prover and run the prover. And the prover goes and runs, and it comes back with a proof of inclusion of the fifth element in this array, or the fifth element of this array, which we conveniently called 5. And we can check that the element is 5 with this verification. Now, again, we cheat a little bit here because we say have the prover just take the Merkle tree from the verifier. A more interesting implementation would be to say have the prover have a Merkle tree inside of its head or its file system and prove inclusion of some element. And that sort of concludes the introduction to 3 different circuit programming languages. And so comments on sort of like what you might think about when choosing these circuit languages. And this is exactly the question. Are these languages tied to certain proving systems and execution environments? The reason that you might choose to use not RISC-0 is it is the most complicated and the most powerful of the 3 sort of circuit programming examples that we went over, but also the RISC-V architecture is an assumption of your RISC-0 prover. So you can simulate RISC-V execution on a non-RISC-V machine, but the sort of question that you might be looking to answer is, could I run the RISC-V proof on a smart contract? And my answer to that is not as far as I know, unless the RISC-0 team is really cooking up some magic. And then you might ask, well, where could I run this RISC-V proof? The answer is, well, you could conceivably run this on any pair of systems that had a RISC-V virtual machine. And I see Bonsai. Someone's mentioning Bonsai, so I might not know everything. So we can talk about, take a look at Bonsai, but it's a place that you can run the RISC-0 virtual machine, as far as I understand, where you would basically have your prover running this virtual machine to prove the code, and then you would have your verifier just check the proof. Now, how much time do I have? Looks like we started about 30 minutes ago, so I probably have like a couple minutes left where I'm running over. Anna, how are we doing on time?
I think you can go as long as you want. We
cool.
don't have any hard stop, and we're also not like, I don't have anything more to present after, so.
Oh, cool. I was trying to slot this for 30 minutes, but I wasn't sure if I was running over.
No.
Cool. Yeah. So looking at other questions, any catches or downsides to RISC-0 just being basically Rust as input? So I mean, like a lot of you, I think, are smart contract interested or smart contract curious. So as far as I know, you wouldn't be able to run your RISC-0 verifier within a smart contract, but I could be wrong about that. I think the reason to go with Circom or Noir is that they specifically target a Solidity verifier and a TypeScript verifier, and they can also be verified from within a C++ verifier. And then Manasi says you can can a prover form a proxy contract on Ethereum? I'm not entirely sure what that means, but generally the way we implement a proving system with respect to smart contracts is that we prove something effectively off-chain, and then we host the verifier inside of a smart contract. So when I say like that you would run some part of the ZK program on a smart contract, I mean that you would be able to, say, automatically compile the verifier to something a smart contract could run. And both Circom and Noir have support for that. And then also, as Broke pointed out, there's a difference between writing a circuit at a higher language or higher level versus a lower level, in that you are going to often get better performance writing at lower level. So increasing levels of level, sort of Circom is very low level, Noir is slightly higher level, and then the RISC-0 prover is probably the highest level that we covered. And so with the increasing degrees of flexibility and power and maybe operation speed that entails. Cool, benchmarks in the chat. That'll be useful to look at. If you were hacking, which one would you take? So I suppose that sort of depends on what I wanted to do. So if I wanted to basically write a circuit that I could then verify in a smart contract, I would probably reach for Noir or Circom, and probably Noir, because it's, I think, especially for hackathons, like speed is of the essence. So you kind of want to get up and running as quickly as possible. But I'm fairly comfortable with Rust, and I quite like the flexibility that gives you. So I probably wouldn't be able to do as powerful or interesting things as, say, proving arbitrary constraints in a high-level programming language like Rust. Or I would be able to do that in Rust, and I don't think I would be able to do that as easily as I would with Noir. And since a lot of the kinds of things that are sort of like out there in the world that are sort of interesting things that you might like to verify, there wouldn't necessarily be a library to do that already for Noir. It would be easier for me to grab Rust and say, verify that some server received an HTTP request or something. Now, if you were hacking, and how are the standard library for each language? Yeah, so that's a good point to talk about. So grabbing down change the window I'm sharing here. And we're going to go with writing circuits. Yeah, so the Circom standard library, the Noir standard library, and the Rust standard library are the relevant comparisons here. So the Circom standard library comes with a couple of circuits that might be of interest to you, including things like signing, hashing, multiplexers, some other lower level circuits. And you would necessarily need to be a little bit familiar with some of these lower level primitives to make sense of them. So if I click into, for instance, compare constant, you can sort of use these as reasonable examples of programs that you might be interested in writing. Same thing is true for Noir, which is a bit younger and has a smaller standard library. The Noir standard library, actually, we were just in. Okay, so I think I must be missing something because there was a lot more that I saw in the Noir standard library, but I could be wrong. Yeah, this might not be the entire standard library because they also implement things like print lines and more. So
actually, maybe a quick note on this is like they will be actually giving a workshop at ZK Hack. So you will have folks on hand who can also help you and answer a lot of this stuff. Yeah, well, there you go. But if you wanted to see examples, the Noir standard lib is probably a good stop for that. And I think their docs are also fairly fleshed out. So if you wanted to take a look at a reasonable documentation for that, maybe printline etc not standard. No, I'm pretty sure it is standard. But I think this might be not the hill that I want to die on for this call. Yeah, the way you use. Yeah. Go ahead. Just wondering, because like this is all meant as our prep sesh. We will be actually in the chats over the next few weeks or the next week, and then we're going to be doing sort of another brief, sort of similar to this next week at the event.
Okay. Cool.
So yeah, I'm just thinking if you want to get more in the weeds on this, maybe it's something we do in the Discord, and we could probably wrap up pretty soon.
Okay. Yeah. And then last, with respect to RISC-0, before we wrap up, you might take a look at these examples in the RISC-0 library. But it being Rust, we demoed using a Merkle tree crate implementation in the example. So you can pretty much use crates from Rust. And they've recently added, or they've been adding more and more support for using the standard library for RISC-0. So that's fairly powerful as well. So yeah, and that's pretty much all I had prepared for you guys. Yeah, thanks everyone for joining, and I hope that was interesting.
I just got a question in the chat that maybe I'll just jump on, which is the how to deal with the Discord channels. So you should have been included if you're coming to ZK Hack Lisbon. You should now have like a yellow name because you've been added to sort of a secret, whatever, like a level in Discord that allows you to see the ZK Hack Lisbon channels. If you haven't, then please send us an email, lisbon@zkhack.dev. It's on our website, on the ZK. Actually, I can share this. ZK Lisbon is the website, so you can always zklisbon.com. That is where you can find more info, the schedule, the partners, and all that. But yeah, the Discord itself, we have an announcement channel, chat, intro and find a team, support, project ideas, travel planning. So feel free to post ideas, travel plans, chat, introduce yourself, kind of what it says there. It is the hub that we're using. So this is all on the ZK Hack Discord. That's like number one step. You got to be there. But I think most of you would be because we only advertise this there. And then you have to be in the secret chats. Yep. Cool. Okay.
Are they zero knowledge chats or secret chats?
Pretty much just secret chats. I don't think Discord's using any ZK tech under the hood. Do you know of any? Yeah. Anyway, maybe one day. Cool. All right. Thanks, everybody. And we see you next week for the kickoff right around this time. So yeah, looking forward.
Mm-hmm.
Bye.
Bye.